This question is related to radiation flux and electricity. So the climate since 2006, the following passage is about the orbiter. The satellite is powered by two solar panels, each is having an area of 9.5 meters square. The panels have high efficiency of 26% of converting the solar energy to electrical. In orbit around the Mars, each panel produces about 1,500 watt of power. Show that when it orbit around the Mars, the power output of a single panel is about 1,500. Radiation flux from a sun is 590 watts per meter square. And area is also given. So the formula which relate the radiation flux is equals to power per unit area. First, we will find how much flux is there. The flux is already given. We have the flux and we have the area. We will find how much power is input. And using that input power, we'll find as I mentioned, we want to show that the power output is about 1,500. So flux is power acting on unit area. So flux multiplied by area will give us the power. The flux is 590 watts per meter square and area is for each is 9.5. So this will give us power, and that power will be the power input. And we need a power output, as they mentioned, it is 26% efficient, like remaining 74% of energy is lost every second and 26% is useful. So 590 multiplied by 9.5, this will give us the power output, which is about 5,600, power input, which is 5,600. Then we will use a formula for efficiency. Efficiency is the useful power output divided by total power input into 100. So efficiency is 26% efficient. Power output, we don't know. Power input is 5,600 and into 100 when we simplify. So it will be 26 times 5,600 divided by 100 will give us the power output, which is about 1,457. So 1,457 watts is the actual power output. The panels are connected together to give a total power potential difference of 32 volts. Show that the maximum power, maximum output current is about 90 ampere. So we have the power which we calculated. The power for each, because we want the total current, so we have the formula P equals VI. This is the power for one solar panel, but because as I mentioned, two are there, so what will the total power? So it will be 1,457 times 2. The voltage potential across the total potential, so that's the total voltage, that is 32 volts, and I we don't know. So it is 1,457 times 2. Why multiplied by 2? Because there are two cells, two solar panels, and each panel is having a power output of 1,457. So combined will be, the total power will be twice as there are two panels. So this will give us the maximum output current, which is 91.25 amperes. This part, the solar panels are used to charge two batteries of capacity 50 ampere hour, means 180 kilocoulombs each. Use the current calculated in part A2 to calculate the minimum time for a fully to charge this battery fully. So the previous answer was 91.25 ampere. That was the total current. Now we want the time. So the total time, as we have the formula, current is equals to charge divided by time. So the time is equals to charge divided by current. So the total charge is 180 kilocoulomb. So I equals Q by T. So T is equals to Q, the total charge divided by current. So it is equals to 180,000 divided by the current, which is 50. The current, it's the total current was there about 91.25. So when we divide this, we'll get the total time it will take to charge, which is 1980 seconds. So this is why the time calculated in B1 is minimum, because we did not consider whenever the charges are moving through. So there is always a heating effect is there, and that produces a heat energy, increases the resistance. So this we consider that the resistance is not changing. In practical, what happened when the battery is charging? So resistance start to increase. As resistance start to increase, so the flow of the charge decrease. So it will take longer time to charge. So, but we assume that the resistance is not changing. So when the component is charging, there is a heating effect. And due to this heating effect, what might happen? The resistance will increase. And due to the increase in resistance, what might happen? It might take longer time than what we have calculated. That's why it is a minimum time, as we assume that the resistance is not changing.